So we're now going to go over some of the statistical techniques we talked about last semester, and of course we're going to start with the t-test for independent and dependent samples. And I think this is a good place to remind us that when we're talking about statistics, we are wanting to basically think of the parable of Occam's razor, and that is that the simplest solution is usually the best solution. So the idea here is that if we have a series of potential choices of statistical techniques that could actually answer the question of the data that we have, we should always go with the simplest one. And this is because as we go through to various levels of complexity, a lot of times we may find that we'll get very similar answers, but the more complex tests are usually designed around the idea of inferring to a more complex question. And they may have adjustments in their mathematics to allow this inference. So for example, an ANOVA is often assuming that you're making multiple tests. You're basically looking at simple main effects, you're looking at main effects, and you're looking at interactions. And it makes some adjustments for this, which means that all you're interested in looking at is a independent variable, categorical with two levels, on a single dependent variable that is continuous. It's best just to use a t-test in that situation. So just as a quick review, the t-test for independent and dependent samples effectively looks at very similar things, and the big question here is whether you have a between groups design, independent, or repeated measures or dependent group design. So the t-test for independent groups, different people in your two categorical conditions, is an inferential test for two groups in a between subjects design. It checks for systematic differences between our group's performance, the DV, and the assumptions are that you have a categorical independent variable with two levels, you have an interval or ratio dV, that you have normal distribution, bell-shaped distribution, homogeneity of variance, so the variance between your two conditions, your two IV levels, are similar. That doesn't mean the means are the same, that means the distributions look similar. And finally, you have independent observations. In other words, you have not only two different groups of people, they actually were not able to influence each other's outcomes on the test or whatever your outcome was. The t-test for dependent groups is an inferential test. So again, it is inferring from a sample to a population for two groups within a within subject design. It checks for systematic differences in the individual performance between within groups. In other words, it's really looking at how each person as a whole systematically changed from one condition to the other. Once again, our assumptions are a categorical IV with two levels, interval or ratio dV, again, a bell-shaped distribution, to some degree, again, homogeneity of variance, that you shouldn't find that you're changing the distributions from condition to condition, simply the means or the average scores. And in this case, you will have dependent observations. In fact, they're supposed to be. They are influencing each other because it's the same people being exposed to different levels of a categorical independent variable. The next thing we talked about was correlation, and we talked about the different types of correlations. And again, correlations examine the relationship between two continuous or dichotomous variables. Now again, that dichotomous is if it's the IV. You can run a correlation with a dichotomous IV. Now, if you have a dichotomous DV, we're not at correlation. That's a non-parametric test, and we really haven't covered those yet. Now, do remember there's three broad types of correlation. The most common is the Pearson product moment coefficient correlation, often just referred to as a correlation. It's what we're normally using whenever we're running correlation, and it is used when both variables are continuous. Well, there is the Spearman correlation, which is an adjustment, and it is not as strong of a test. And what I mean by strength here is it is less likely to declare a difference to be statistically significant. So if possible, we always want to use a Pearson correlation if the data is appropriate to it. But what a Spearman correlation allows us to do is it's used if we have ordinal data, again, as our IV. And you cannot necessarily use a parametric statistic in this situation. So a Spearman correlation is going to be used a lot of the times when we actually have ordinal data. So the numbers do have rank, but we don't have equal distance. We're usually going to see Spearman's correlations work better when that ordinal data has a lot of different scores. In other words, it would be very cumbersome to make that a categorical variable using a different statistical technique. The other possible use of a Spearman correlation is that we have non-standard data. In other words, The Spearman correlation does not have the assumption of a parametric or a bell-shaped curve. So if you are trying to run a correlation on data that is non-normal, and the simple tests or simple ways to try to get that data to become normal aren't working or not appropriate for your data set. In other words, you don't feel comfortable dropping certain scores, you don't feel comfortable necessarily doing a mathematical correction. You could change that continuous data into rank data, ordinal data, and then run a Spearman correlation, which doesn't have the assumption of normal distributions. Finally, the point biserial correlation is used when one of those variables is continuous, our DV, and our IV is dichotomous. Again, it's categorical, but only 2 levels. And if we run one of those, technically what we're running is a point biserial correlation. As a quick note, if you run a point biserial correlation alone, in other words, it's not a part of an initial series of tests, the p-value produced would be the same p-value you'd produce if you use that same data set looking at a t-test, which also looks at a dichotomous IV categorical on a continuous DV. So correlations, remember what they do is they measure the association between variables. The value reflects the strength of association and can range from +1 to -1, 0 being no relationship. Remember, the sign simply reflects direction, not strength. So a -0.9 is a stronger relationship than a +0.5. If it is a negative sign, that means it's a negative correlation. As one variable increases, the other one decreases. If there's a positive sign or no sign, that means it's a positive correlation. As one variable increases, so does the other. The test statistic calculated is R, and effect size is probably one of the easiest ones to calculate. We simply square R, and that tells us the percent of variance explained. It tends to be independent of the scale of measurement, and by that what I mean is that regardless of how your IVs and DVs are measured, on a 1 to 10 scale, on a 1 to 100 scale, on a 500 to 722 scale, you are still going to, at the end of the day, be given an R that ranges between 1.0 and -1.0. So once we actually find out if it's significant or not, we do need to know that effect size, the meaningfulness of the correlation, and this is referred to as the coefficient of determination, or simply effect size, which is, again, your test statistic, R squared. So for example, if we had a study, an example of a study looking at studying test scores, and they were correlated at an R of 0.88, we would multiply 0.88 times 0.88. We'd square it, which would give us an R squared of 0.77. What this means is that 77% of the test score was predicted by the amount of study time. That would be a very strong relationship. And whatever is left is the proportion of unshared variance, 1 minus R squared. So 23% of test score was not related to studying. As a general rule of thumb, you're going to find different rules of thumb on all effect sizes, but across the sciences, what you'll usually find is something close to this, that an R squared of 0 to 8% is usually a weak relationship. So if you're explaining only 8% of the variance in behavior or an outcome, that's weak. 9 to 48% is a moderate, and over 49% is a strong relationship. Now, recognize that this is across all sciences, and honestly, in a lot of applied settings, if you can explain 8% of human behavior with a predictor, that's probably going to result in good outcomes. It's better than guessing. So if I actually knew that a particular predictor predicted my outcome, let's say reading ability, by 8%, so it explained 8% of reading ability, that might be a variable I very much would want to attend to when designing classes and designing interventions. So don't get locked down in these scores. Recognize that the meaningfulness of an effect size is always relative to the actual cost of the intervention and how much likely it is that you're actually going to see good outcomes. When we move to regression, the only thing we're adding over correlation is that regression allows us the ability to predict in future samples. So it's a one-to-one relationship. For any point in a line of X, there'll be a corresponding Y. So once you run a correlation, what it is saying is you can use that correlation to, in the future, predict someone's outcome score if you know their predictor score. So again, we have a sample. We measured in that sample both the IV, X, and the DV, Y. But now we want to use that information to predict future Ys. And what we're going to do is we're going to calculate the slope in our original sample to determine the change in y, our outcome, per unit change in x, our predictor, whether it's a positive or negative relationship. The y-intercept or constant is where that regression line crossed the y-axis. In other words, if x was 0, what would y start at? This is the equation that we're interested in. And error is more theoretical. What is the amount of expected variation from the predicted estimate? Now, we can later go back and actually predict error. So if we actually were using the predictor scores on someone to predict their y, once we actually had their y, we could find out how wrong we were, and that could give us a better estimate of error. Our predicted estimate is y hat or y prime. So again, if we have our a, what would our y be if we were at 0? We have the person's score in x, and we know how much y increased or decreased for each unit increase of x, b. We simply do the equation. Constant plus b times x, that gives us our predicted y. Now, when we move from simple to multiple regression suggests that there are 2 or more predictors of our outcome. And these variables can include just about anything. They can include linear trends, so what we normally look for under normal conditions. They can include covariates, variables that we want to actually measure to remove. They can include continuous variables, which is easy to do, but they can also include categorical variables. If that categorical variable is dichotomous, we don't have to do anything. We can put it into a multiple regression. However, if the categorical variable has 3 or more levels, we can still use it. We simply have to dummy code it into dichotomous variables, multiples. We can look at nonlinear trends, and we can look at interactions. And we can look at all of these in a single statistical test. So there really is no limit on the number of independent variables that we include in a multiple regression. The only limits there is our sample size. Do we have enough people to have this many variables? Basically, again, a good rule of thumb is 10 people per variable. Probably a better rule of thumb is close to 20 per variable. And also recognize that as we make a more and more complex model, we also are making it less and less likely that we find small effects. Additional predictive variables mean that we must now consider how each predictive variable relates to each other, as well as how it relates to the DVs. Now, when we're calculating regression coefficients in a multiple regression, we do need to think about power. And again, as we add additional predictors, we are reducing our degrees of freedom. We're making it less likely to find statistical significance. And generally speaking, we want to make sure that we're adding a minimum of 10 subjects per variables we add. So if I'm starting with a correlation, 1 IV and 1 DV, I probably want at least 20 people. If I go up to a second IV, we want to probably have at least 30. If I add a third IV, we probably want to go to 40 and so on. We do also want to recognize that as we add additional predictors, we're wanting to make sure we're adding predictors that are not highly related to the other predictors and are at least predicted to be related to our outcome. Multiclinearity is when we have too many independent variables and they're more related to each other than our actual outcome. So basically, are we measuring the same construct with different variables? Are we losing power but not really gaining any prediction? Not only is that a problem that we're making a more complex model that's less likely to find statistical significance, we also will start to find that because multiple regression can look at the variables in different orders, depending on the order we look at it, we may get very different results if there is high multiclinearity. If we find significant relationships in a multiple regression, we do need to look at effect sizes, and there's basically 2 types. Semi-part or partial correlations, which is, again, the unique variance explained by our predictor in all of the variants of our outcome, or partial correlation, which is the unique variance explained by our independent variable on the unexplained variance in our DV. And both of these may be useful, and which one you're going to use is usually based on what questions you're asking. And finally, when we actually run a statistical test in SPSS, regardless of the type of test we're running, we're generally looking for a couple of things. We're looking for the error, and this is going to be where some of our degrees of freedom are coming from, and it's usually the bottom of the equation. It's the unexplained variance. It's the variance that we don't have an account for. And then we're going to have the actual DIVs, in this case 1 IV, study type. That's going to be our effect. And again, if we go down this chart, we'll see our 2 degrees of freedom for the effect, which gives us an idea of how many conditions there were in that effect. and the degrees of freedom for our error, which is usually based on sample size. We're going to get our mean squares, and again, this is the final calculations of all that variance. The top one, study type in this case, is our effect, and the bottom one is our unexplained error. We're simply going to divide our effect by our error, and that's going to give us our test statistic in some form. In this case, an F statistic, because this is an ANOVA, 14.932. We'll also find out if it's significant, and if it's significant, we'll also get our effect size. So again, just kind of recognize how this process is happening across all statistics when we're looking at SPSS readouts.